afternoon, good evening, good morning, good night to all of my continents: Asia, Europe, Africa, North America, South America, Australia, New Zealand, Antarctica. Hopefully I didn't miss anybody. Europe, did I say Europe? Thank you so much if you're joining. Welcome, welcome, welcome to tonight's live on string theory. Is it wrong? Is it right? What is going on with it? What is the deal with the extra dimensions in string theory? This is what we're going to discuss today. Some of you have been leaving some interesting, intriguing comments on my channel, and for this I think it is a good time to talk about the extra dimensions of string theory. Ooh, there's Fuji Baba playing behind me. Hello, Stephen. So today I've decided that I will use the first 20 to 30 minutes of the live to just kind of do my spiel on the topic. It's going to be string theory and its extra dimensions, and I'll give you a little spiel, I'll give you a little summary. And then I will be addressing all of your comments and chat messages in more detail once we're 20 to 30 minutes into the live. And I'm gonna try to say I'm gonna do my best to try and say hi to everybody that's joining. Hello, Stephen. Hello, Umid. Umid says salam alaikum. Wa alaikum assalam. How are you doing? Hello, Stephen. Hello, Umid. Hello, everybody that's going to be joining. Stephen says, I want to say thank you for the other night when you read my book. Of course, Stephen, my friend, thank you so much. And there is Fuji behind me. Thanks to the universe, thanks to God, and touch wood, all of that. So today what we're going to do is we're going to continue with the string theory topic that we have been pursuing for a little while from the book, The Elegant Universe by Brian Greene, and especially because we have been getting certain questions on the channel that have to do with, is string theory a piece of fiction? Is it something that even makes sense or not? Does it have infinite dimensions? Why does it continue to be such a topic of interest? And is it even anything that we should sort of bother to learn about or not, etc., etc. I also want to point out that I am not exactly an advocate of string theory or an expert in string theory myself. I'm just a student here to learn like you. It is not the topic that that I did my PhD in, so in no way am I an expert of string theory. So I'm kind of referencing authors and books and things like that and learning together with you. It's more of a study with me, booktuber, book talk, book club kind of vibe that's going on with this topic here on YouTube, okay? I also want to say that when the topic is my expertise, I'll let you know about that as well, such as particle astrophysics, which has more of a particle physics and astrophysics type of flavor, then that is actually in my area. So I'll let you know when that happens as well, okay? You can theory on, oh gosh, well, Ford, hello. Hello, Stephen. Hello, Umid. Hello, Ford. Hello, everybody. Thank you so much for being here. Please do like the live. Can we get 20 likes? Can we get 30 likes? Can we get 40 likes? Thank you so much. But I will do my best to kind of keep the content a little bit tight so that the people who are watching the video later on as a video upload, which by the way, I implore everybody to do that. Please do see this video later on if you're missing the live and can't quite make it to the live time, but please do go back to the channel. Thank you so much, Stephen, for liking the live. Thank you so much, Ford, and everybody who is here. Please do like the live. Can we get 20 likes? But if you're seeing this as a video upload later on, I'm going to keep the content and give you my spiel within the 20 to 30 minutes of the beginning part of the live stream so that you can get that value right away, okay? Thank you so much once again for being here. Welcome, welcome. Thank you so much indeed for being here. Good morning, good afternoon, good evening from all parts to all parts of the world, from all parts of the world, here, right now. Okay, let me share the live on my other device so that people know that we have indeed gone live, and we will now get started. So as I look at my phone, let me just say once again that we're going to be discussing string theory tonight. We have been discussing this for a few live streams now. If you go to my channel under the live tab, you will see several of the lives that we've been doing have been sort of on similar or relevant topics or related topics, either string theory, supersymmetry. We've also covered particle physics, quantum mechanics, and especially the history of how physics developed and modern physics developed in the 20th century, especially we have taken a lot of time to discuss that back in the past lives, okay? So if you're new to the channel, please do feel free to go look back in time and find these live streams which have a lot more explanations and discussions on what I just said: particle physics, quantum mechanics, general relativity, special theory of relativity, sort of the developments of the 20th century, as I like to call it, sort of, especially, for example, the year 1905, when Einstein gave us like 4 amazing different things, including but not limited to mass energy equivalence and the relative nature of space and time. And of course, he gave us special theory of relativity in that year. He also contributed to what we call the old the old quantum mechanics, which is basically understanding the quantum, acknowledging, discovering, understanding the quantum nature of light, which is of course photons. So he also gave us photoelectric effect. This is what he actually got his Nobel Prize for, because a lot of people didn't really understand his relativity work. Okay, so he worked on special theory of relativity, which works only for inertial frames. Then he generalized it more and got it more broader, with broader applications, and also including accelerating frames. And he gave us general theory of relativity as well soon after 1905, sort of still in the early 1900s. So you will see how there was a little bit of development of string theory soon after general relativity came out. In the year 1919, there was some important developments by Kaluza and Klein, 2 people that we've kind of mentioned in the channel before. We will talk about them more again tonight. Hello 710 Seaman, how are you doing? Stephen, hello. Ford, hello. Everybody, hello. So you will see how we're going to kind of talk about that as well again tonight, because that will give you a flavor of the extra dimensions that we're going to talk about with string theory. And especially because some people on the channel, once they saw my older live streams, had asked about, well, string theory is they were basically questioning the validity of string theory based on its requirement of these extra dimensions. And at some point, I think I read the word infinite dimensions, but I do want to point out that I believe, even though I'm not an expert on string theory, and we will do the reading in just a bit to confirm all of this, I do believe that it's not infinite dimensions, but it is extra dimensions, or hidden dimensions, or what's another word? Curled up dimensions, extra dimensions, hidden dimensions. It is more dimensions than what we are used to. We live in 3 spatial dimensions, and there's the time dimension. So all total, we generally acknowledge 4 dimensions, including time. But string theory basically requires extra spatial dimensions, but it's not quite infinite dimensions. So I just want to clarify that right away before we go too far into the topic tonight, which is that it's not, as far as I know, infinite dimensions that they speak of, but more like extra dimensions, extra spatial dimensions. I believe it's around 9. Okay, so it's around 9 extra dimensions, not necessarily infinite dimensions. The other thing is that I will say one piece of value that one might always get out of string theory is that it is based on general theory of relativity. So if you are wondering about string theory and its validity, one place to really start is general theory of relativity. And for that, if you need to first do special theory of relativity, be a student of that, then feel free. This is really what I would recommend, is that if you want to do the study yourself and you want to probe these questions on your own, then you first need to understand the relativity topics, right? Whatever Einstein did with special theory of relativity, and then take that forward to general theory of relativity. And once you kind of understand those, I think you will see how it kind of gives a natural progression or a permission to include more dimensions to string theory. So the people who worked on string theory didn't just get it out of nowhere. They were kind of taking general theory of relativity and progressing it to include more spatial dimensions. So it didn't just come out of nowhere. There is sort of a progression, there is sort of a history, there is sort of a context that they're following. And these people are generally very good at the math, and they're good at general theory of relativity. So, and GR is something that has definitely stood the test of time. It's not a completely correct theory. There are some issues with it as well. There are issues with both sides of physics that are generally dueling each other, the physics of the very large, which is general theory of relativity, and the physics of the very small, which is quantum mechanics. And by the way, because these this particular fragmentation of physics is something of an issue, where general theory of relativity and quantum mechanics, physics of the very large and physics of the very small, don't quite merge together very well. They don't unify very easily. They have certain sort of perpetuating conflicts or quarrels that are still kind of unresolved, and people would rather have a more broader general theory that can explain all of this, sort of a theory of everything. This is actually why we have string theory. String theory is a candidate for a theory of everything. You may like it, you may not like it, but it is sort of that is the need of it, that is the motivation of it. So when string theorists are writing their research grants for why they should be paid money to do string theory research, this is because they want to do a grand unification theory or a theory of everything, because they want to unify the two quarreling sides of physics, once again, which is general theory of relativity on the one hand and quantum mechanics on the other hand, both of which were of course developed in the 20th century. So the 1900s were a very, very rich time in progressing our insights and physical insights, especially into physics, astrophysics, cosmology. So again, those types of historical developments that we have talked about on the channel before is something that would be a wealth of knowledge, hopefully, to anybody who is interested in that, okay? So having said that, this is really the basis. The point of string theory is that it is a grand unified theory candidate. If it were not a grand unified theory candidate, I doubt that anybody would really care about it. Nobody is sitting there wanting to deal with extra dimensions and making their lives harder with already hard math and making it even harder, because as you can imagine, if general theory of relativity deals in 3 spatial dimensions and 1 time dimension, of course, extending that to include more spatial dimensions, even if it's just 1 more spatial dimensions, even though general relativity may allow that, it doesn't necessarily make your life any easier, right? You do have to do the math very carefully and kind of do this difficult work. So if this was, if torturing yourself was a hobby, then one could see how, people would do this, but they're highly motivated to do this because they're trying to explain something bigger. They're trying to unify general relativity with quantum mechanics, and they're trying to get a bigger, broader theory to explain some of the effects that we see, for example, in quantum mechanics, which cannot be explained by general relativity, okay? General relativity does not explain, for example, quantum mechanical effects like the probabilistic nature of quantum mechanics, or spin, the property of particles that we have discovered. And quantum mechanics cannot be remember that if general relativity could just say that quantum mechanics is wrong and we should forget it, then it would. But quantum mechanics cannot be forgotten because there is a lot of experimental evidence to the effect of giving us quantum mechanics outcomes and results and particles and these discoveries that keep happening, including but not limited to, of course, the Higgs boson in 2012, and before that, so many other particles, right? Proton, neutron, quarks, all of those particles being discovered, giving sort of confirmation and validation and further and further and further proof that quantum mechanics is good. Quantum mechanics is something bizarre, but it does give us all these results that are experimentally proven. So quantum mechanics didn't go away. That's the thing. There were bizarre developments happening to the effect of people discovering quantum mechanics and further making more and more discoveries under that topic. And general relativity cannot explain quantum mechanics. And so general relativity is considered more of a classical theory, whereas quantum mechanics is, of course, a quantum theory. Quantum versus classical, right? This classical versus quantum battle is still a thing. It was very much a thing. People did not like quantum mechanics from the classical camp. And their theory, though, could not explain some of the things that were coming out of quantum mechanics. And because of the evidence and because of the experimental successes of quantum mechanics, they could not ignore it either. So they wanted a theory of everything. They wanted a grand unified theory, or a GUT, a theory of everything. You might have heard of that term. And a candidate for that, once again, is string theory. This is the motivation for string theory, so we cannot completely ignore it. But long story short, once again, I think I titled the live stream as "Is String Theory Wrong?" The answer is we don't know. As far as I know, the answer is that we don't know. We don't know if string theory is wrong. We don't know if string theory is right, because string theory is so far not testable. But I wanted to tell you all of these words above because this is what's going on. This is the motivation. We want a theory of everything. A candidate for that is string theory. Is string theory right? We don't know. Is string theory wrong? We don't know. Is string theory testable? So far, no. Okay? So that's what's going on. We will learn a lot more details going forward in this live from the book, directly from a string theory author, Brian Greene, Green with the extra E at the end. Brian spelled normally like the B-R-I-A-N, Brian Greene, who wrote The Elegant Universe, Superstrings, Hidden Dimensions, and the Quest for the Ultimate Theory. So this quest for the ultimate theory is what motivated the work in string theory. Hello, Jay. And this quest for the ultimate theory is why people stomached these sort of extra dimensions, hidden dimensions, and sort of the more stranger quirks of string theory. Because those dimensions, having the extra dimensions was allowed by general relativity, it's almost like, because you might say, well, what is so bizarre about quantum mechanics? Depending on who you are, you'll either find string theory very bizarre or you'll find quantum mechanics very bizarre. The classical theorists or the classical physicists found quantum mechanics to be very bizarre. Quantum mechanics and its uncertain nature, its probabilistic nature, finding a ton of particles all the time, discovering more and more particles without an overall explanation of what it all meant. Those people thought quantum mechanics was bizarre. Quantum mechanics people probably think that string theory is bizarre because string theory has all these extra dimensions that and makes it impossible to test. So it's basically a point of view that we must be aware of. We must educate ourselves to know, like, everybody is a little bit biased. Everybody comes from their own points of view. And so when you're being taught physics and when you're being, when you read the news or you hear some announcement or you learn some piece of information, always kind of keep in your mind what the source is and what they're trying to say and what sorts of context and points of view they might be coming from. So classical physicists think that quantum mechanics is kind of weird, and quantum mechanics people think that classical physics is kind of weird, especially when you talk about string theory, having all these extra dimensions. Classical mechanics, the stuff we need to understand gravitation, the planetary motions, the laws of motion, and the moon orbiting the earth and the earth orbiting the sun, that stuff is not so weird. That is just Newtonian mechanics. It's been well understood for centuries. But once Einstein gave us deeper insight into gravitation in the form of his relativity theory, and then once that was extended further to also give us string theory, that is where it gets quite weird. And a lot of people, especially who believe in experimentation, who believe in observation, who believe in experiment being the sort of center, the core of physics, where physics is an experimental science, right? Those people will, of course, snatch the money and the research grants away from theories that are obviously not testable, right? So you can see how people can be very competitive when they're presenting these ideas. I wanted to give you sort of an unbiased as I can be type of view on all of this on this channel, because we discuss all kinds of topics on this channel, not just the topics that I study personally, but just in general, we try to cover physics, astronomy, astrophysics, and cosmology. And when it comes to cosmology, which is one of my favorite topics to learn about and talk about as well and to share about, we have to obviously talk about general theory of relativity. You can't escape it. And it's a very beautiful theory. And when you talk about general relativity, it's a natural extension to also talk about string theory, because string theory is the candidate for what Einstein was trying, okay, after general theory of relativity. So that is sort of where we are. Hello, Oliveira. I'm going to share the live. I don't think I ever did that. And we will keep on keeping on. So, but once again, the summary is string theory does not have infinite dimensions. As far as I understand it, it has 9 spatial dimensions instead of the 3 that we know and love and are used to and familiar with. It is it's motivated by unifying the 2 parts of physics that are currently not unified, which is general relativity on the one side and quantum mechanics on the other. It's more of a classical theory based on general relativity, and general relativity does allow you to have extra dimensions, so why not, said these people who are good students of general relativity. So side note, if you ever want to take a class on GR, you should definitely go to a string theorist and ask them to teach you, because they'll be very good at it, as far as I have experienced. And thirdly, is string theory wrong or right? We simply don't know because it is not testable. Okay? So, hello, Bera11. How are you? Bera says, school me. Of course, gladly. Gladly, honey. Stay on and we will, as soon as I've shared the live, we will get back into this topic. Okay? Thank you so much, everybody, for being here. Hello again, B-A-E-R-A, Bera11 says hi. Thank you so much, everybody, for being here. Much appreciate. And if you're seeing this as a video upload later on, I do hope that you will... Hello, Backpack, how are you doing? Hello, everybody. If you're seeing this as a video upload later on, please do like, share, subscribe. If you found this and you don't know about this is a channel on cats and physics, and under the physics topics, we generally cover, especially during these live streams, we cover physics topics, astrophysics, astronomy, cosmology, and we also cover kitty cats and more casual videos like that. But the live streams, we try to give more value in the form of these physics lessons and topics, which is also my background. Okay? And thank you so much, everybody. It's a bit quieter here on Saturday. Usually these live streams have a lot of people, a lot of chat messages happening, lots of engagement, people who join and become friends with each other, people who join and contribute their own thoughts and comments and everything like that. Would you watch a tree grow? Hello, Backpack. So that's what generally happens. Today's Saturday, but I took a couple of days off. I was kind of tired from speaking a lot, but and I had some other things going on that I had to work on. So I wanted to post and do a live tonight and further the topic that we've been covering, which is string theory and its extra dimensions. But if you're seeing this as a video upload, please do like, share, subscribe. Leave your comments. Always appreciate reading your comments later on from the people who watch this later on. Thank you so much, Heike, my friend, and everybody else. Hello, Jay says, so J-E-Y, thank you so much for being here, and I see your comments, and I do appreciate it. Thank you so much. I think I saw you asked me how I'm doing earlier, and thank you so much. Okay, so we will try to keep it tight and give you the topic straightforwardly tonight's live, so that when you're listening to this later on, you get a lot of value and don't have to deal with a lot of interferences, okay? Because I know that sometimes the live streams can be a little crazy and get a bit off topic. But we do our best. It is fun to also engage with everybody who is attending the live stream live, right? So that's sort of the balance that I try to achieve here. But once again, thank you so much for being here. We will keep on keeping on. Hopefully the spiel I gave on string theory and its relevance, its motivation, and sort of the status of where it's at in terms of being testable, etc., whether it's right or wrong, hopefully that part is already clear to you by now. And we will now keep going. So now remember that Kaluza-Klein had worked on sort of extra dimension stuff, like basically proposing that maybe general relativity equations could be done with one extra spatial dimension. They were being kind of modest in their proposal of only adding one extra spatial dimension, because as you know, we end up with around 9 spatial dimensions in string theory, by the time it's been developed further. But in the year 1919, so quite early on in the 1900s, shortly after general theory of relativity came out and Einstein gave us that and contributed further in terms of relativity theory and equations and math and all of that, Kaluza-Klein Kaluza-Klein had worked on this and proposed it and told it to Einstein. So I want to point out that string theory's sort of father is general theory of relativity, and this work by Kaluza and Klein is quoted as being important because they were sort of the first people who kind of took general relativity and sort of dared to extend it a little bit beyond what we are generally familiar with. Because even proposing one extra spatial dimension is quite a bit of a departure from what we generally would be familiar with, because generally we think of generally we think of our experience to include just the 3 spatial dimensions and just the 1 time dimension. Having anything more than 3 spatial dimensions is already a bit of a stretch or a bit of a departure from what we are familiar with, and you know, you might start to be very uncomfortable with that. A lot of people are very uncomfortable with that, but because general theory of relativity already sets up the math in a way where you can actually add dimensions, so they thought, why not? And they kind of took this leap, and then it kind of did not go anywhere right away, but it was sort of revived as an idea, and really string theory developed more fully in the 1960s. Okay, so unfortunately this is after string theory, I mean, as in string theory was developed in the 1960s after Einstein's death, so he didn't really get to enjoy it in its full glory. And also remember, we've kind of talked about in the last few lives that in the beginning string theory was kind of struggling, and certain issues with it were very troublesome. But of course, as time went on and they worked on it more and more, they worked on those issues. And of course, there were some other assumptions and things that they needed as well, such as supersymmetry, for example. Remember, that's another thing, by the way. If they keep looking for supersymmetry and don't find it, then that would also be something that goes against string theory, because I do believe that superstring theory, which is the supersymmetric string theory, which is what you kind of need for string theory to work, depends on supersymmetry. Okay? Stephen, hello, thank you so much. So this is the sort of where we're at, and now we're going to talk about extra dimensions, and that is sort of motivated or contexted by the Kaluza-Klein work. Okay, so keep in mind that why physicists, who are obviously going to talk to you about string theory, why they want to tell you about Kaluza-Klein is so that it doesn't seem so crazy and so sudden when they propose extra dimensions later on. So they're basically trying to make the point that, remember, Kaluza-Klein said there was 1 extra spatial dimension back in 1919. So we're not crazy to revive that or bring that back, or basically propose even more extra spatial dimensions in the 1960s, because remember, Kaluza-Klein did that already, and Einstein had sort of blessed them. Now, how much of a blessing Einstein really gave, we will see. We will see what Brian Greene has to say about that. We don't really, I don't know if we really know fully. But at the same time, it wasn't totally discarded as something nonsensical or as something like awful. So that is some level of confirmation or validation for proposal of extra dimension, okay? And remember that when people are trying to develop a new theory, of course they're going to latch on to everything that will sort of support it, right? Because it's not a testable theory, or at least not a very easily testable theory. So just remember that, of course, every piece of evidence that may give it any strength at all, every piece of every little thing that may give some support will be highlighted, will be latched on to. And this is sort of how physics is done. It's a little bit like making a case for something. It's a little bit like being a lawyer. So just think about it. Think about the current section that we're on as sort of being a lawyer for extra dimensions in physics, being a lawyer for extra dimensions in string theory, or being a lawyer for extra dimensions in nature, right? You want to start and make your case, and you want to start with, remember in 1919 what happened? Kaluza and Klein did this, and they said this, and then Einstein said this, and remember what they actually found, and then kind of carry it forward. If you don't reference the people who have worked on things before you and achieved some level of success, that's just going to be really tough, okay? So this is why literature search and sort of telling people what's been done already is the most important thing in physics or in research, because that's what you're building your case on. So quite literally think of it as building a case, right? Where you're maybe defending extra dimensions. Maybe you're a, I don't know, criminal lawyer who is defending extra dimensions going to jail or not, okay? So unification in higher dimensions. So sometimes this is called higher dimensions, sometimes higher dimensions, sometimes this is called extra dimensions, sometimes these are called hidden dimensions, sometimes these are called curled up dimensions, or the extra ones at least anyways, okay? So although Kaluza's 1919 suggestion that our universe might have more spatial dimensions than those of which we are directly aware was a remarkable possibility in its own right, something else really made it compelling. So Kaluza, once again, are things okay? Can you guys hear me, by the way? Is the screen shaking or anything like that? And is the audio good? I just want to make sure real quick. Thank you so much for being here. So remember that Kaluza had proposed an extra dimension back in 1919. Einstein had formulated general relativity in the familiar setting of a universe with 3 spatial dimensions and 1 time dimension. So being 3 spatial, 3D in space and 1D in time. Hello Saksh, how are you? So having, so this is the Elegant Universe by Brian Greene, and we're currently on the topic of string theory and its hidden dimensions or extra dimensions, sort of building a case on having these extra dimensions, whether they make sense or not, etc. And you might want to rewind and start from the top, okay? Because we've been kind of talking about it in a bit of a summary already. So if you want to catch the full topic, please do rewind when you join partway through. So basically, Kaluza has had already done the work of extending general relativity a little bit. But, hello, but, thank you, Stephen. So, but, the nice thing is that Einstein, by the way, Einstein was actually a very intuitive guy. Like he was a theorist, he was a theoretical physicist, but he was very much grounded in nature and reality. He wanted to he wanted to make sense of this universe, but in an intuitive way, in a way where you can do thought experiments, where things make sense. So he knows, obviously we know that we live in 3 dimensions spatially. So he's not really the type of guy who likes mathematics enough to start with, oh, let me add an extra dimension, throw it in the mix and see what happens. He's not really that guy. Kaluza is that guy. Klein might be that guy, right? Some other mathematician might be that guy. But Einstein is actually much more of a physicist with his heart in physics more than in mathematics, okay? Saksh says, Jeff says, make America great again. Hello, Jeff. Hello, Saksh. So Einstein is definitely got his heart more in physics. He wanted to give us an updated theory for gravitation, an explanation of gravitation, and accelerating frames, because special theory of relativity, of course, gives us an explanation of physics, but in inertial frames. So you have to be going at a constant velocity or be at rest in order for your physics to be explained by special theory of relativity. So to generalize that, he gave us general relativity, right? Literally, it's general relativity versus special case of relativity. So now gravitation is allowed. Now gravitation has to be explained, because remember, gravitation makes us accelerate, right? So what is gravitation? That is explained by general relativity by Einstein in the 3 spatial dimensions and the 1 time dimension. And he had already told us that space and time are relative. And now in general relativity, he's basically saying that the bending of space-time is gravitation. Gravitation is not regarded as a force necessarily in general relativity. It is the curvature of space-time. So more massive an object, it's going to curve the space-time around it the even more. And in fact, he also predicted gravitational waves from like big explosive gravitational events like cataclysmic explosions, supernovae, black hole mergers, neutron star mergers, and we have even started to measure gravitational waves now, much later. Once now we have the technology to measure gravitational waves, almost I think it was over 100 years after Einstein first predicted them. So general relativity, once again, has a lot of experimental success. A lot of the predictions of general relativity have come true, been shown observationally. But ultimately, it was very much a theory that was trying to explain the physics, and his heart was all about trying to explain the nature and the physics. It wasn't so much about making everything a math problem, right? That's not really Einstein. He was very much more grounded in the sort of physics things. So he didn't do this. He did general relativity, and the mathematics allowed for more dimensions, but he kept it as a 3D space and 1D time type of theory. It was Kaluza who modestly added one dimension. Modest in the sense that at least he didn't add many more dimensions, but he did add one. So it was a leap already to go from 3 spatial dimensions to just adding the 1 spatial dimension. But you can see how if you say that adding 1 spatial dimension is okay or allowed, then why not add a few more? I think currently we have the 9 spatial dimensions in string theory, and that's how they are going to make this math work and give us properties that are seen in quantum mechanics, because remember, string theory is about unifying general relativity with quantum mechanics. Okay, so Einstein did not, however, formulate it in the way of extra dimensions. Einstein formulated general relativity in the familiar setting of a universe with 3 spatial dimensions and 1 time dimension, like a good boy that we know and love, because we understand 3 space dimensions and 1 time dimension. That is nothing new there. But even with that, GR is a little hard, as somebody noted, because GR is still in the 4 space time, where it's like the 3 space and the 1 time dimension are sort of on an equal footing in the mathematics, right? So it's still not easy mathematics when you do general relativity. It's a little bit different. You have to kind of change your realm of mathematics to do the math a little differently. You have to define things like the metric, the geodesic, all of that, which, by the way, we talk about in a different live quite a while ago. Okay. The mathematical formalism of his theory, however, could be extended fairly directly to write down analogous equations for a universe with additional space dimensions. So this is where he wrote down general relativity for the 3 space and the 1 time dimension, but it can actually be extended to include more spatial dimensions pretty easily. And by easy, I mean it's not really that easy. It's not like 1, 2, 3, 2 plus 2 math, but it's allowed, it's allowable. Okay? So under the modest assumption of 1 extra space dimension, Kaluza carried out the mathematical analysis and explicitly derived the new equations. So Kaluza, as a good student of general relativity, which, by the way, most, if not all, string theorists are, they start with general relativity and then they extend it. That's really what's going on. He found that in the revised formulation, the equations pertaining to the 3 ordinary dimensions were essentially identical to Einstein's. This is another thing. Once you extend general relativity to have, say, another extra dimension, you still have to prove out Einstein's work and show that in your new theory, Einstein's work is all still valid, right? If the equations don't look like something totally different or give you a different kind of universe, then that's not good. You should be able to explain the general relativity universe. It should fall out smoothly from your new theory. Okay, because again, remember, the whole point is to unify GR with quantum and explain all of that with one theory. So if your one theory cannot explain some part of what is already known, then you would look very bad. Okay, so that's what's going on. But because he included an extra space dimension, not surprisingly, Kaluza found extra equations beyond those Einstein originally derived, which makes sense. So extra dimensions means extra equations, extra math, got it, right? It's fine. After studying the extra equations associated with the new dimension, Kaluza realized that something amazing was going on. The extra equations were none other than those Maxwell had written down in the 1880s. So in the 1800s, that was a great time for electromagnetism to have leaps and bounds of progress by, of course, people like James Maxwell, Michael Faraday, etc. So anyway, you might be familiar that Maxwell has given us the equations of electromagnetism, but when he did this extra dimension thing, he got Maxwell's equations for describing the electromagnetic force, which was very exciting, very exciting. And they all kind of knew that Einstein, a grand unified theory, should basically spit out GR, electromagnetism, quantum mechanics, all of this, right? So isn't it so great when that starts to happen? So that's another thing when somebody pointed out, is string theory just a fake news or sort of a fiction? Well, the thing is that they wouldn't have, for example, at the point at which we are right now, Kaluza-Klein, right? They wouldn't have progressed things if they didn't see some hints of nature and some other things being able to get pulled out of doing this extra dimension stuff. If the extra dimension stuff led to total nonsense, then they wouldn't have carried on with it, right? So that's part of it too. It's that they did see some light at the end of the tunnel, otherwise they wouldn't have gone in that route, because nobody's trying to look stupid or crazy, right? So by adding another space dimension, Kaluza had united Einstein's theory of gravity with Maxwell's theory of light, which is a great success. So imagine, I mean, if that was your PhD thesis, for example, and you did some crazy thing, and by crazy I mean in a good way now, say you took Einstein's equations, you added one more dimension, and somehow you got Maxwell's equations out. I mean, that would be pretty impressive. That would give people pause to think like, oh my gosh, like, is this how, is this what's going on? Like, is there an extra dimension thing on which that we don't experience? And then if you consider it, you get one more theory out, and here's your grand unification of at least GR with electromagnetism. Now all we have to do is to also unify quantum mechanics, which is the strong nuclear force and the weak nuclear force as well. And maybe if that can come out too, we would be really happy. So this is sort of like people got greedy for the theory of everything. It's like once you start to see that something is working out in one way, which is the electromagnetism thing, you get greedy for a theory of everything. What if we got a theory of everything out, right? And now I'm not saying that things didn't get much more complicated with that. Definitely it did. But you can kind of see the train of thought here, and people have to follow their train of thought once they see that glimmer of hope for unification, okay? Before Kaluza's suggestion, so before Kaluza's time, or before this suggestion that he did with the extra dimension, gravity and electromagnetism were thought of as two unrelated forces. Nothing had even hinted that there might be a relation between them. And remember once again that when we talked about unifying the non-gravitational forces under that very extreme environment of the extreme temperature or extreme energy or very tiny dimensions, remember we talked about this one live ago or 2 lives ago, that was still about the unification of the non-gravitational forces. Unifying something like gravity with the non-gravitational forces had not seen the light of day, right? Basically, we have seen examples of unifying the non-gravitational forces, that is between the three, that is electromagnetism with strong and weak nuclear forces. So there's the electromagnetic force, strong nuclear force, and weak nuclear force. We've seen some work and some progress in unifying these three, but we had not seen progress in unifying these three with gravitation. So any glimmer of hope that unifies those with gravitation would definitely give people pause and at least be something that they would think about. So another thing here to keep in mind, why did string theory pick up again in the 1960s after this was done by Kaluza in the year 1919, which is pretty early on in the 1900s, is because they had this glimmer of hope. Afterwards, when they were all working on unifying the forces and they saw how difficult it is, and even unifying the non-gravitational forces, because like the other thing is too that during Einstein's time or earlier in the 1900s, they didn't have enough information. The discoveries of certain things were not done yet, right? Even the neutron was discovered kind of later on. I think it was like 1930 something, 1932 maybe. So remember that first of all, one of the issues was that not everything was known. Like, what are you going to unify if you don't even know about it, right? But when they were trying to unify things, eventually, after more things were discovered, such as the neutrons, such as the quarks, such as more particle physics, they found it was incredibly difficult. It's not easy to unify the fundamental forces and have one broad, simple explanation for them. It's very difficult. You have to go to some very extreme temperatures, energies, or scales to unify the three non-gravitational forces, which are electromagnetism, weak nuclear force, and strong nuclear force. It's very difficult. So once they then remembered, remember in the year 1919 when Kaluza-Klein had done this crazy thing of adding an extra dimension, and they had unified gravitation with electromagnetism. That is too exciting. That will lead people to have a lot of greed for the theory of everything, because that gives them a little hope that, oh my gosh, maybe it can be done. You know what I mean? So extra dimensions may seem like a crazy idea to the normal people, to us, the normal public, but it's not crazy when you follow the train of thought of those physicists who were doing this work, okay? Hello, MSTR Ronan. Thank you so much. Thank you for joining. Welcome. Can someone do a super chat? That would be very amazing and helpful, and thank you. Thank you everybody for being here. So before Kaluza's suggestion, there was no unification between gravity and electromagnetism. They were considered to be two unrelated forces. Nothing had even hinted that there might be a relation between them. By having the bold creativity to imagine that our universe has an additional space dimension, Kaluza suggested that there was a deep connection indeed. His theory argued that both gravity and electromagnetism are associated with ripples in the fabric of space. Ripples in this fabric of space. Gravity is ripples in the fabric of space. Gravity bends space-time. Electromagnetism also travels through space. Light can travel through a vacuum, right? Light is oscillating electric and magnetic fields. It travels through a vacuum. Remember, because there was, in the past, remember, before Einstein gave us special theory of relativity, there was confusion about how light travels in vacuum, remember? Because people were like, oh, is there something called ether? And then Einstein's work did away with all of that because light can travel through a vacuum. It's an electromagnetic wave. So the fact that these two things that are both ripples in space or waves traveling through space may have some kind of unification, if you just add one extra dimension, was incredibly powerful. It gave a lot of hope to people who were interested in unifying these forces, okay? So gravity is carried by ripples in the familiar three space dimensions, while electromagnetism is carried by ripples involving the new curled up dimension. So he basically invented a new curled up dimension, this Kaluza guy, and told us that gravitation is carried by ripples in the familiar three space dimensions, which is what was explained to us by Einstein with his general relativity, and this curled up dimension that he came up with might just give us electromagnetism. It did, actually. So Kaluza sent this paper. So he's got this paper now, and he sends it to Einstein. And at first, Einstein was quite intrigued. On April 21, 1919, so over 100 years ago, it's the month of May now, but just imagine last month, April, but over 100 years ago, Einstein receives this paper of his general relativity, but extended to include one extra spatial dimension by this guy Kaluza. And so what is Einstein's reaction now, right? Einstein wrote back to Kaluza and told him that it had never occurred to him that unification might be achieved through a 5-dimensional, 4-space and 1-time cylinder world. So remember, Einstein always talked about 4D, which is including time, so the 3-space plus the 1-time dimension. So now Kaluza, with his extra space dimension, is giving us a 5D world. He added, at first glance, I like your idea enormously. About a week later, though, Einstein wrote to Kaluza again, so he probably thought about it more. This time with some skepticism. I have read through your paper and find it really interesting. Nowhere so far can I see an impossibility. So he basically probably looked for a mistake in Kaluza's work and couldn't find one. By the way, if you're joining, can you please like the live? Can we get 10 likes? Thank you so much. On the other hand, I have to admit, Einstein said, that the arguments brought forward so far do not appear convincing enough. But then on October 14, 1921, more than 2 years later, so he, I guess, thought about it for 2 more years, Einstein wrote to Kaluza again, having had time to digest Kaluza's novel approach more fully. I'm having second thoughts about having restrained you from publishing your idea on a unification of gravitation and electricity 2 years ago. If you wish, I shall present your paper to the Academy after all. Belatedly, Kaluza had received the master's stamp of approval. So apparently he hello Jamie, that's what we're talking about. So apparently Einstein digested Kaluza's theory for 2 years before basically accepting his paper and saying that he's willing to give a talk on it and help to publish it, which is pretty cool. So sometimes if your work is denied or rejected, maybe just give it 2 years and then maybe it will get approved, who knows. Although it was a beautiful, because I think he probably looked for the mistake and couldn't find one. And also I think it was very intriguing to him that there is any kind of unification between gravitation and electromagnetism. Little did he know, of course, that there's going to be more fundamental forces later on that are discovered. Some of these discoveries happened after his death, Einstein's death. So of course he's missing some of the information that is not yet discovered, but just even having this unification between gravitation and electromagnetism is a big glimmer of hope, because he has already set his mind to it. And he's already kind of thinking about the theory of everything and thinking of how to unify these forces, okay? And so are other people. Let's talk some string theory, says Jamie. That's what we're doing. Although it was a beautiful idea, subsequent detailed study of Kaluza's proposal, augmented by Klein's contribution, so he worked together with another person called Klein, showed that it was in serious conflict with experimental data. The simplest attempts to incorporate the electron into the theory predicted relations between its mass and its charge that were vastly different from their measured values. So there was some issues with what this new theory, the 5D theory from Kaluza-Klein, what this found and what was known experimentally about electrons' mass and charge. Because remember, so hello Bears TV, hello Jamie, hello everybody. If you could be, please be supportive and polite, and can you please like the live, and can we get 20 likes, and can you do a super chat? That would be amazing. Somebody asked about tying a ponytail. You could do a super chat of $500,000 for that. Otherwise, just sit down and listen to the physics. Thank you so much. Welcome so much. So basically, remember that when you're trying to unify GR, electromagnetism, all of this with quantum mechanics, see, electron is obviously something that's involved in electromagnetism, right? It has electric charge, etc. But electron is also something that is known in quantum mechanics. It's also known as something as a particle, right? Electron is also known experimentally as a particle. So the thing is that quantum mechanics and particle physics, I was mentioning earlier, why did these topics, I can't call them theories exactly because they're experimentally proven, they're experiments as well. They're both theories as well as experiments, right? Quantum mechanics is not just a theory. Particle physics is not just a theory. They have a lot of experimental proof associated with them. So even though people didn't like quantum mechanics and particle physics, how come they survived? How come, right? It's because of their great experimental success. So we experimentally knew about the mass and charge of the electron. So if your new grand unified theory, or just any not so grand unified theory, basically this 5D theory is a not so grand unified theory, right? It's an attempt. It's sort of an attempt at something, and it's a good work. It's a good piece of work. There is merit to it. Not taking away any credit from Kaluza-Klein back in 1919, they did a very creative piece of work. Acacio, thank you so much. Thank you for the super chat. Thank you so much, Acacio. Hello. Thank you, thank you, thank you, thank you, thank you, thank you. Much appreciate. Thank you so much. If you want to do a super chat, guys, and ladies and gentlemen, anybody who's here, much appreciated. Really, really appreciate you. Thank you so much. But remember that not taking away any merit from the Kaluza-Klein work in 1919, because they did a very creative thing. So we have to appreciate the creative work that was done in 1919 and adding this 5D, giving us this 5D world. Adding this extra spatial dimension is important. But at the same time, it's not quite the very much grand unified theory that we would like, because first of all, it unifies gravitation and electromagnetism, and we know that there are more fundamental forces. There's actually two more fundamental forces. And the other thing is, if your new theory does not properly predict something that is known in experiment, then it's going to be refuted. That's actually how you get stomped on. That's actually how you die as a theory. It's very unfortunate. It's not to say that the work was anything bad, but experiment is king of the jungle, especially when experiment is possible. So anytime something can be experimentally proven, first of all, you want to, pursue that experiment or a series of experiments to let your theory go through those things and be an experimentally proven theory, right? And second of all, if it fails to satisfy experiment in the sense that it predicts something and the experiment gives you a different answer, then it needs to be updated. It needs to be worked on further, or it's just gonna die. Okay, and that is the brutal nature of experimental science, obviously, right? JEY, you might wanna be more polite than that, darling. Okay? Thank you so much, everybody, for being here. Thank you for your support. Thank you so much. I really do appreciate all of you. Thank you so much for the super chats. Thank you so much for the views and the likes and the shares and the subscribes. The people who do support this channel obviously help to keep it going, so I wouldn't want anybody to be rude to those people. Thank you so much. Okay, so so this is the unfortunate, but also sort of this is also what gives physics its merit, though, right? It's because of that cold clinical nature of experimental proof that either disproves your theory or proves your theory, that actually gives physics its credit. If we didn't prove things out experimentally and we just kept on going with any old theories, any thoughts of ours, that would not be good either, right? So it's fine. The thing is, it's fine to have your theory be wrong. You just need to keep working on it, keep updating it, and match with experiment, and keep that conversation open with experimental work. Okay? Hello, lover toy pups. Hello, and how are you? Thank you so much for being here. My friend Lover Toy Pups is here. Thank you so much for the hearts, and thank you so much for the emojis. Really appreciate you. So this is kind of what happened, is that his theory did not match up with electrons' mass and charge, which honestly, it probably just meant that it needed to be updated. It did not necessarily mean that 5D is wrong. It just means that there's probably something there that he needs to update. So The thing is, one shouldn't get discouraged when there is such a failure or such a sort of setback, right? And I think we'll see some more to that effect here. So because there did not seem to be any obvious way of getting around this problem, which is the not matching of the mass and charge of the electron, many of the physicists who had taken notice of Kaluza's idea lost interest. So unfortunately, if your work is not supported, then that could also kind of kill it. Einstein and others continued now and then to dabble with the possibility of extra curled up dimensions, but it quickly came to be an enterprise on the outskirts of theoretical physics. I mean, to be honest, string theory is still sort of in the outskirts of theoretical physics or just physics in general. It is it is in the theoretical side of things, first of all, because it's not really experimental work or experimentally testable work, and the less the thing has to do with experiment, the more it will continue to live on the outskirts, right? So that's another sad truth as well about these theories. But anyways, with the Kaluza theory, the nice thing though is that at least something with experiment happened with the Kaluza theory, right? Because actually, it's not a failure. If you say something and it's experimentally proven to be wrong or needs an update, that's actually still progress towards finding more truth. Because it could be that the theory that you came up with is just a partial truth, right? Or it's a truth that needs updating. It's not, well, it's a lie kind of, but once it's updated, it could be a truth, right? So when experiment comes in and tells you something, when experiment comes in and tells you something that kind of challenges your theory, what that means is that you just need to update your theory. So you have to work closely with experiment in order to do that. Okay? So again, not a failure in terms of finding the truth though, right? If a theory is there and experiment shows something which challenges the theory, we're still getting closer to the truth, which is a good thing. Hello Doro, how are you doing? Thank you for coming. Thank you for being in the live. And can we get 10 likes? And can we get 20 likes? Thank you so much. So this extra curled up dimension business basically kind of went away. For a while because of the experimental evidence coming in and challenging this theory. Okay? In a real sense, Kaluza's idea was way ahead of its time. The 1920s marked the start of a bull market for theoretical and experimental physics concerned with understanding the basic laws of the micro world. So basically, people were very much invested in quantum mechanics is what he's trying to say. I mean, the camp of people who wanted to see more progress in quantum mechanics, of course, was going to see more progress in quantum mechanics and go for more quantum mechanics results and work happening in that time. And I mentioned earlier already that the 20th century or the 1900s were very rich. On the one hand, we got relativity. On the other hand, we got quantum mechanics. Those two did not see eye to eye, but one of them is to explain the very large, and the other one, of course, is to explain the very small. And these are very important developments, though, that happened in the 20th century, which are worth understanding. And I think it's a very interesting historical journey indeed, if you discuss all this, which we have in the past on this live. So it's like very, very interesting. But probably the classical physicists did feel that there was more interest in quantum mechanics because everybody kind of sees what's happening to the other people. If there is something happening on the other camp and they're getting more money or more support to do research, of course, this camp is going to be like, those people are getting more attention. So it's sort of that, and it could be true that, because Kaluza's theory gave us the wrong mass and charge of the electron, it was just kind of stomped on, But as a theory, maybe it just needed to be updated versus completely killed. Hello, Doro. Thank you so much for your kind feedback. So, theorists had their hands full as they sought to develop the structure of quantum mechanics and quantum field theory. Experimentalists had the detailed properties of the atom as well as numerous other elementary material constituents to discover. Theory-guided experiment and experiment-refined theory as physicists pushed forward for half a century, ultimately to reveal the standard model. So this is the standard model of particle physics. So what he's saying here is something that I was just now saying earlier, which is that basically if you're going to come up with theories, it's good to work closely with the experimentalists and the experiments so that your theory can be updated accordingly. If there is things that are being found in experiment that are going against the theory, then you want to update and further work on your theory, because a theory is not an end-all be-all. It shouldn't just stay stagnant. It should be constantly getting updated and worked on, and you should be paying attention to the experiments that are happening, and if there's something that challenges your theory, you should be working extra hard to address that and updating your theory. Your theory doesn't have to stay where it was, right? And this is basically what happened within quantum mechanics and particle physics world, the other camp, the camp opposite to the classical physicists, and they came up with the standard model, which is the standard model of particle physics. So, theorists had their hands full as they sought to develop the structure of quantum mechanics and quantum field theory. Experimentalists had the detailed properties of the atom as well as numerous other elementary material constituents to discover. Theory-guided experiment and experiment-refined theory as physicists pushed forward for half a century. So it's like 50 years of glory to quantum mechanics and particle physics, giving us more and more information, more and more discoveries, and theorists and experimentalists working hand in hand together to give us better theories, more refined theories, and experiments that either confirm or refine them, okay? Ultimately to reveal the standard model, which is of course this big thing that gives us the families of particles, or basically the standard particle physics model gives us the leptons, the quarks, the bosons. We've talked about them, families of particle physics and details about that, okay? It is no wonder that speculations on extra dimensions took a distant back seat during these productive and heady times. So lots and lots of work on particle physics and not as much work on string theory or extra dimensions during this time, okay? So between 1920 to around 1960s, there was not really much happening with string theory or extra dimension work. Hi from Australia. Hello, stuff happening. How are you doing? Thank you so much for being here. Hello, Australia. Hello, New Zealand. Hello, Antarctica. Hello, Southern Ocean. Hello to my Southern Hemisphere, South America as well. As I greet Australia here, I will greet the other people. And how is the southern sky? Can you see Little Dipper in the sky? And is the Coriolis force flushing the water the other way? I think the southern hemisphere is a lot of fun. And also, how are the spiders in Australia? Hello, thank you so much. Welcome, everybody. Madagascar and Africa, oh my gosh, you're right. Acacio, thank you so much. I forgot parts of Africa are, of course, in the southern hemisphere too. I am so sorry indeed. Stephen, congrats on your book and looking forward to chapter 2. Doro, thank you so much for being here. Acacio has reminded me of Madagascar, and of course, parts of the African continent is in the southern hemisphere as well. I'm so sorry for missing that. Lovely. Looking forward to your drawings, Stephen. Okay, so basically, between 1920 and the early 1960s, there was not much going on in the form of extra dimension work, which is what string theory needs as a grand unification candidate. So that's what the author here is saying, is that people were too busy with quantum mechanics and particle physics. And mind you, these topics were very successful. There was a lot of experimental success in these fields. And so, of course, they progressed, of course, they advanced. And of course, we came up with all of this more progress in those fields, okay? So anyways, speculation or work with extra dimensions just did not have too much breakthrough between 1920s and 1960s. Good night, Doro. Thank you so much. So, with physicists exploring powerful quantum methods, the implications of which gave rise to experimentally testable predictions, there was little interest in the mere possibility that the universe might be a vastly different place on length scales far too small to be probed by even the most powerful of instruments. But sooner or later, bull markets lose steam. By the late 1960s and early 1970s, the theoretical structure of the Standard Model was in place. By the late 1970s and late or early 1980s, many of its predictions had been verified experimentally, and most particle physicists concluded that it was just a matter of time before the rest were confirmed as well. Although a few important details remained unresolved, many felt that the major questions concerning the strong, the weak, and electromagnetic forces had been answered. The time was finally ripe. You are now redeemed from your sin of not mentioning Madagascar. Oh my gosh, thank you so much. Acacio, are you from Madagascar? Is that where you're from? So, the time was finally ripe to return to the grandest question of all, the enigmatic conflict between general relativity and quantum mechanics. And so, this is when people decided maybe we can go back to this original question and remember Kaluza-Klein. Remember those bold people who had injected one extra dimension and shown some progress in unifying gravitation with electromagnetism. Now, there were some things about that theory that was kind of wrong because they got the electron mass and charge wrong, but oh well, things happen, and maybe they should have just been given the opportunity to update their theory and refine it further if they were given that opportunity, or research grants or money or time or energy of day. So I think this is kind of where people started to go towards. Poor Kaluza-Klein, So the time was finally ripe to return to the grandest question of all, the enigmatic conflict between general relativity and quantum mechanics, the success in formulating a quantum theory of three of nature's forces emboldened physicists to try to bring the fourth gravity into the fold. So another thing is, which did not happen by the time Kaluza-Klein were doing their extra dimension stuff, is that the unification of the non-gravitational forces that I mentioned earlier, the unification of electromagnetism with strong and weak nuclear forces when you go to some very extreme temperature, energy, or length scale, very tiny length scale. We spoke about that. Remember, it was this unification that then required a little bit of help or a little touch of supersymmetry at the very end in order to be good, right? In order to really truly unify those three. So this unification work happened later on, right? Later in the 1900s. So this was not there when 1919 was happening and Kaluza-Klein was doing the extra dimension stuff with Einstein's general relativity. So this also made people more bold and wanting. It's kind of like you already did 3 or 4 different chores out of 5 then you feel much more emboldened to do the fifth chore and just be done, right? And so because they had already unified the 3 of the 4 fundamental forces, now of course they want to keep going and try to unify gravitation with the 3 fundamental forces that are already sort of unified under particle physics, supersymmetry, and all that. Hello, Grimmy. Thank you so much for being here. Can we get 20 likes? Okay. So, having pursued numerous ideas that all ultimately failed, the mindset of the community became more open to comparatively radical approaches. So, at first, they tried some things that were not as radical, and then they went towards sort of the more radical approaches. After being left for dead in the late 1920s, Kaluza-Klein theory was resuscitated. So, this is basically now string theory coming back to life in the 1960s, and really the father or the people who had given it some life back in the 1920s, all the way back in the 1919 and not published until 1929, 1921. 2 years after 1919 is 1921. Sorry, just got something in my eye. Thank you, Grimmy, and thank you, Stephen. So basically, even though they kind of left the Kaluza-Klein theory for dead back in 1920s, just because it kind of was wrong about that electron mass charge thing, but nonetheless was a pretty creative and good attempt at something, and saw some progress in terms of unification between gravitation and electromagnetism, but it kind of got left behind, and instead people focused on quantum mechanics, particle physics, and all of the experimental successes that came from those. But now that 3 of the 4 fundamental forces saw progress in unification and gravitation was still not unified with those 3, people started to think, oh my gosh, what do we do now? And it was interesting again to think about unifying these forces and to think about, well, what can we do to unify and try all the simple stuff. That doesn't work, and maybe we have to go back all the way back to Kaluza-Klein's work, which we left for dead in the past, but may have to sort of resuscitate. So that's what's going on with string theory and its extra dimensions. The context and the foundation of the extra dimension was already there back in the 1920s, soon after general relativity was given to us by Einstein. So it's not completely new, and basically string theory is a modern day Kaluza-Klein theory, because 1960s is quite a bit after 1920s. So for 50 or so years, nothing with string theory, and then finally it's kind of resuscitated. So that's the context, and that's the foundation of string theory and it having extra dimensions. As you know from this live, that Kaluza-Klein gave us extra dimension, extended general relativity, if you will, which is sort of a father to string theory. But it was kind of wrong, so it needed updating. And also, obviously, if you don't work on something, it's not going to get updated on its own, and it's not going to get there with explaining more things and being more correct, and including more explanations, for example, explaining all the different types of particles and particle states and quantum properties like spin, etc. So basically taking all that and then giving it more sort of an extension is what will be happening now. But that's the base of it. The base is what we just discussed. The base and the foundation is that general relativity allows you to incorporate extra dimensions, and Kaluza and Klein were bold enough to do that in the year 1919, and even it was published in 1921, and Einstein gave it a look, thought about it, could not really find mistakes, but or really something wrong with it conceptually, but it did not have experimental success. Now, when a theory does not have experimental success, doesn't mean that it's instantly wrong. It means that it needs more work, it needs to be updated, and it needs to be refined with experimental support, right? And the theory and the experiment should be supporting each other and working with each other. Of course, they have to get along in order to do that. Usually the theorists are not the same people who design and build and run the experiments. So they have to get along and they have to work together. But without that too, the theory will kind of die, right? And that's exactly what it did. It did die until it was time for it to be kind of revived again, which is what's going to happen in the 1960s, which is what we'll talk about next. Does gravity have any effect on the microparticle field? On the microparticle field? Well, gravitation will work on anything that has mass. So all of the particles that are massive are affected by gravitation, and in fact, light is even affected by gravitation. So depending on if your gravitational field is very strong, even light will be bent. So yes, I think I'm not exactly sure what you mean by microparticle field, because particle physics in general is microscopic. There's a lot of really tiny particles, subatomic particles, microscopic or small, if you will. So if you're asking if gravitation has anything to do with the particles, then the answer would be yes. Gravitation has something to do with massive particle physics. Gravitation has something to do with anything with mass, especially, but also gravitation is the curvature of space-time. So gravitation actually, in general relativity, which is a correction to Newtonian mechanics. I was going to say Newtonian relativity, not relativity, but Newton's gravitation was giving us a theory for gravitation already. Einstein's gravitation is the general theory of relativity, and so it tells us that gravitation can be thought of as a curving of space-time by massive objects, and even light is affected by that. Particles are affected by that. Yes. I like this little starfish ring I have. It's looked a little. It's going, thank you. Okay, so by the time people are talking about working on string theory and doing this extra dimension stuff again, which had died, good night, Grimmy, which had died until the 1960s, after 1920s. By the time this is happening, there is leaps and bounds of progress that happened in physics already, in the form of quantum mechanics, particle physics, experimental successes, discoveries, etc., etc. So it's a very different landscape now, a very different landscape than what Einstein was familiar with when he was alive and doing work on grand unification theory, etc. So it's kind of a shame that Einstein was not able to oversee the efforts of string theory because it happened later on, right? But at the same time, maybe it's okay that string theory picked up again later on, because by then more experimental outcomes were known of already. And remember, the more that's known, the more you have to explain with your theory, right? If you're coming up with a more general, grand, unified theory, of course you have to now be responsible for showing even more facts and experimentally proven things, because if you have a theory and you cannot explain what's already known from the experiments, for example, the mass and charge of the electron, say as an example, then you're going to be stomped on and your theory is at risk of dying unless you quickly or rapidly update it, refine it, etc., etc. It's like the machinery has to be sort of in place, right? So let's see. I think this is very exciting. So anyways, the understanding of physics had significantly changed and substantially deepened in the 6 decades since Kaluza's original proposal. 6 decades? That would mean 60 years. I thought, okay, maybe this is a little later than what I was thinking. Okay, whatever. Quantum mechanics had been fully formulated and experimentally verified. The strong and the weak forces unknown in the 1920s. So again, strong and weak forces were not even known in the 1920s when Einstein had just come up with or just contributed general theory of relativity and all that, okay? So the strong and the weak forces unknown in the 1920s had been discovered and were largely understood. Some physicists suggested that Kaluza's original proposal had failed because he was unaware of these other forces and had therefore been too conservative in his revamping of space. So it could be that is it could be that because remember, actually yeah, remember that the strong and weak nuclear force actually do affect how we perceive the electromagnetic force, especially at different length scales. Because remember how we were talking about okay, well, remember how we were talking about Acacio says, I want to say in quantum physics. Remember how we were talking about sort of this cloud around, you know, the nucleus. The components of a nucleus interact with each other with a strong nuclear force, right, at the tinier length scales. So it's almost like when you consider the electromagnetic force between, say, the electron and the nucleus, it's like the electron and sort of this fuzzy thing, ball of stuff that also interact with each other. So the strong nuclear force actually does affect how you measure things, and it may contribute, like you might have to account for certain corrections because of the strong and weak nuclear forces if you're gonna be trying to be accurate or precise about the electromagnetic forces. So it could be that Kaluza did not know, right? I mean, he wouldn't have known in 1919 about the strong and weak nuclear forces because those were not discovered yet. So it is a shame. It is a shame. Things are not always known, so that could be part of the problem. It's still, your work still has merit, Kaluza and Klein. So anyways, let's see what he's saying about that. Some physicists suggested that Kaluza's original proposal had failed because he was unaware of these other forces and had therefore been too conservative in his revamping of space. More forces meant the need for even more dimensions. More forces meant the need for even more dimensions. It was argued that a single new circular dimension, although able to show hints of a connection between general relativity and electromagnetism, was just not enough. One second, let me think about that. Hello, lol machine. What's the topic for tonight? It's string theory and its extra dimensions and sort of the foundation of that. That's the topic for tonight. Okay, so it was argued that a single new circular dimension, although able to show hints of a connection between general relativity and electromagnetism, was just not enough. By the mid-1970s, an intense research effort was underway, focusing on higher dimensional theories with numerous curled up spatial directions. There is a little picture here of that, which illustrates an example with two extra dimensions that are curled up into the surface of a ball that is a sphere. As in the case of the single circular dimension, these extra dimensions are tacked on to every point of the familiar extended dimensions. For visual clarity, we again have drawn only an illustrative sample of the spherical dimensions at regularly spaced grid points in the extended dimensions. Beyond proposing a different number of extra dimensions, one can also imagine other shapes for the extra dimensions. For instance, we illustrate a possibility in which there are again two extra dimensions, now in the shape of a hollow donut that is a torus. Although they're beyond our ability to draw more complicated possibilities, can be imagined in which there are 3, 4, 5, essentially any number of extra spatial dimensions. So by the way, at the end of the live, I'm going to show you these pictures, so just hang tight. We'll skip a little, and the most promising of the higher dimensional proposals were those that also incorporated supersymmetry. So that's the other thing. Remember that string theory actually had certain difficulties if you did not incorporate supersymmetry, and this is why the author of this book, Brian Greene, had made a case for supersymmetry prior to bringing that in for how you need that for string theory. So this is another sort of detail, is that superstring theory is actually supersymmetric string theory, and supersymmetry kind of lets string theory be able to explain more and kind of hold in more cases. So physicists hoped that the partial canceling of the most severe quantum fluctuations arising from the pairing of the superpartner particles. Basically, the superpartner particles help with those quantum fluctuation shenanigans. Why do charged particles produce electromagnetic waves? Is there any answer in string theory? Is there any answer in string theory? We will definitely, that's a great question. Hello Ritesh. Hello Venom. Venom Man. Hello. Hello Ritesh. So that's a great question. I have to give it more thought. Posed like that, that is actually very intriguing. But let me just remind you, because of this section that we're in, that the supersymmetry comes in because remember how the quantum fluctuations of the pairs and the virtual pairs causing fluctuations actually basically make it harder and give you more things to consider when you are at those tinier scales. And the super partner particles, because supersymmetry basically gives all the particles a super partner particle, those actually help to cancel out some of these fluctuations, which help with some of the calculations in string theory. So that's why string theory needs supersymmetry, and because it needs supersymmetry, then it's called superstring theory. And that's another thing, by the way, if you have something against string theory that you might want to attack it with, is asking to prove supersymmetry, which I believe that they are trying to do that with the Large Hadron Collider. So it's one of the things, you know, if we found super partner particles, then that would give us evidence of supersymmetry. If we don't find super partner particles, that would put constraints on supersymmetry, and it would put constraints on string theory to some extent, I would imagine. So physicists hope that the partial canceling of the most severe quantum fluctuations arising from the pairing of super partner particles would help to soften the hostilities between gravity and quantum mechanics. They coined the name higher dimensional supergravity to describe those theories encompassing gravity, extra dimensions, and supersymmetry. So supersymmetry definitely important for this obviously superstring theory. So again, supersymmetry proving or disproving would be very important to string theory. Okay, as had been the case with Kaluza's original attempt, various versions of higher dimensional supergravity looked quite promising at first. The new equations resulting from the extra dimensions were strikingly reminiscent of those used in the description of electromagnetism and the strong and the weak forces. But detailed scrutiny showed that the old conundrums persisted. Most importantly, the pernicious short-distance quantum undulations of space were lessened by supersymmetry, but not sufficiently to yield a sensible theory. Physicists also found it difficult to find a single, sensible, higher dimensional theory incorporating all features of forces and matter. It gradually became clear that bits and pieces of the unified theory were maybe surfacing, but that a crucial element capable of tying them all together in a quantum mechanically consistent manner was missing. Because remember, the bosonic string theory is what I believe came out in the I forget, it was 1960s or 1970s. And that string theory, the bosonic string theory, was missing the fermionic string theory. But of course, fermions are a thing. So if your theory doesn't include fermions, then that's also kind of bad. But at the same time, I want to mention that whenever some theory does something and it's challenged by experimentally known things or challenged by experimental work or outcomes, that's not the end of the world for that theory. They just have to be updating their theory, they have to refine their theory, and they have to see like what to do in order to make it hold. And basically, I believe that it was supersymmetry that helped superstring theory, or string theory at that point, needed to become superstring theory in order to survive some of the brutal truths of quantum mechanics. So, and brutal because if it's known experimentally and you cannot explain it, then that's going to be bad news for you as a theory. So in 1984, this missing piece, string theory, dramatically entered the story and took center stage. Because people were trying in other ways to see if there could be some unification between gravity and quantum mechanics. And they had seen more results coming out of quantum mechanics and particle physics. Here's Sachi Mama. Hello Ashar. Hello Ritesh. Hello Venom. Hello everybody for being here. So basically the supersymmetry stuff is important in more ways than one. It seems that there was a time in the 1970s and 1980s when they tried hard to do something to unify gravitation with quantum mechanics, with other theories, and that didn't really work. That didn't really help. Ashar says, I study astrophysics a lot. Very good. That's great. Me too. So eventually now they're gonna partly it's the successes of quantum mechanics and particle physics that gave us more and more information, which remained still ununified, not unified with GR. And parts of it is the failure to unify things with other methods. And part of it was that somebody had been bold enough to propose extra dimensions already in the past. Remember, Kaluza-Klein, that's the foundation of this work. The author has made sure to tell us about that again and again. And hello Ashar, hello Nirmal, how are you doing? And then part of it is that basically, if you get desperate enough to unify things and there is not another theory that can instead explain or do the job, then they're going to go back to the more dimensions and the extra dimensions. It's almost like they're emboldened by the previous effort. They're emboldened by more and more being found in quantum mechanics that is still not unified with general relativity, and they're emboldened by the fact that other theories have not done the job of unification either. Okay? Are you cat lover? Yes. Yes, indeed. Yes, indeed, my friends. Thank you so much for being here. Welcome, welcome. Thank you so much. By the way, can everybody please like the live? If you could please like, share, and subscribe, that would be amazing. I can make a note of that and cover it another time. I'm about to wrap up actually. So, let me see. Let me finish with a little bit more on the dimension stuff, since I said I would talk about that. And by the way, if you're joining, you should definitely rewind and go to the beginning of the live, okay? So, the author says, by now you should be convinced that our universe may have additional curled up spatial dimensions, certainly, so long as they are small enough, nothing rules them out. Basically, this is to say that if there may be some hidden, curled up, tiny dimensions that we don't experience, so far, nothing really rules them out. But of course, we understand that if we come up with a theory, including them, the point of that theory would be to unify gravity with the other forces, with quantum mechanics, particle physics, and of course we expect the outcomes that are already known in those fields to come out of this theory. We cannot just ignore things that are already known, right? But extra dimensions may strike you as an artifice. Our inability to probe distances smaller than a billionth of a meter permits not only extra tiny dimensions, but all manner of whimsical possibilities as well. Even a microscopic civilization populated by even tinier green people. While the former certainly seems more rationally motivated than the latter, the act of postulating either of these experimentally untested and at present untestable possibilities might seem equally arbitrary. So at least the extra dimensions are very tiny. And so the point is that, well, these extra dimensions are so tiny we can't possibly probe them experimentally. But also that means that they are not disproved either. It would be a problem if you said something as part of your theory and that could not be and that goes against something that is experimentally shown. But if you hypothesize something that cannot be experimentally probed at all because of our current state of technology, then at least it's not disproved. Okay? Such was the case until string theory. Here is a theory that resolves the central dilemma confronting contemporary physics, the incompatibility between quantum mechanics and general relativity, and that unifies our understanding of all of nature's fundamental material constituents and forces. But to accomplish these feats, it turns out that string theory requires that the universe have extra space dimensions. So string theory, it's not just optional in string theory to have these extra spatial dimensions, it's required. So, hopefully the people who, want to support string theory, even though it's not testable, which is fine, I guess, likes the fact that it has these extra spatial dimensions because those are a requirement here, okay? So one of the main insights of quantum mechanics is that our predictive power is fundamentally limited to asserting that such and such outcome will occur with such and such probability. So he's reminding us of the probabilistic nature of quantum mechanics. Although Einstein felt that this was a distasteful feature of our modern understanding, and you may agree, it certainly appears to be fact. Let's accept it. Now, we all know that probabilities are always numbers between 0 and 1. Equivalently, when expressed as percentages, probabilities are numbers between 0 and 100. So if it's a percentage, it would be a number between 0 and 100. If it's a fraction, it would be a number between 0 and 1. Physicists have found that a key signal that a quantum mechanical theory has gone haywire is that particular calculations yield probabilities that are not within this acceptable range. For instance, we mentioned earlier that a sign of the grinding incompatibility between general relativity and quantum mechanics is in a point particle framework is that calculations result in infinite probabilities, which is really bad. As we have discussed, string theory cures these infinities. So string theory with all its extra dimensions apparently will cure these infinities and these bad numbers of probabilities and will restore them to be good numbers. But what we have not yet mentioned is that a residual, somewhat more subtle problem still remains. In the early days of string theory, physicists found that certain calculations yielded negative probabilities, which are also outside of the acceptable range. So at first sight, string theory appeared to be awash in its own quantum mechanical hot water. So, sometimes general relativity and quantum mechanics in point particle, the bad thing can be both very big numbers that are infinite probabilities. That's not good either in quantum mechanics. And if you have negative probabilities, that's not good either in quantum mechanics. And if you're coming up with answers that kind of go against experimentally proven quantum mechanics stuff, then that's not good for your theory. So you have to save your theory updated, find the issues, and address those issues, okay? With stubborn determination, physicists sought and found the cause of this unacceptable feature. The explanation begins with a simple observation. If a string is constrained to lie on a two-dimensional surface, such as the surface of a table or a garden hose, like we've given the example of that garden hose, remember, where one of the dimensions was curled up and we couldn't see them zoomed out, see it zoomed out. So anyways, if a string is constrained to lie on a two-dimensional surface, such as the surface of a table or a garden hose, the number of independent directions in which it can vibrate is reduced to 2. So the number 2. The left hand and back fourth dimensions along the surface. Any vibrational pattern that remains on the surface involves some combination of vibrations in these two directions. Correspondingly, we see that this also means that a string in Flatland, the garden hose universe, or in any other two-dimensional universe is also constrained to vibrate in a total of 2 independent spatial directions. If, however, the string is allowed to leave the surface, the number of independent vibrational directions increases to 3, since the string then can also oscillate in the up-down direction. Equivalently, in a universe with 3 spatial dimensions, a string can vibrate in 3 independent directions. Although it gets harder to envision, the pattern continues. In a universe with ever more spatial dimensions, there are ever more independent directions in which it can vibrate. There's Sachi Mama, you can look at her while we read. So basically, the giving it more dimensions, the theory basically getting more dimensions gives more dimensions of independence to the string and how it can vibrate. We emphasize this fact of string vibrations because physicists found that the troublesome calculations were highly sensitive. So they must have found this when working on this, that this is highly sensitive to the number of independent directions in which a string can vibrate. And basically vibrating strings, oh my gosh, well, something has broken beside me. The kitty cats are having their zoomies. I'll get to it. The vibrating strings, if I'm not mistaken, in string theory kind of give us the different states and quantum states and whatnot. So being able to vibrate in many ways is sort of needed by string theory. So if you limit its vibrations too much or don't let it vibrate independently in many dimensions, then it's not going to do a good job of explaining many things. And remember, string theory has many things to explain. It's trying to be a theory of everything. It's trying to be a grand unification theory that unifies GR, or general relativity, with quantum mechanics. So all of the things that were found in quantum mechanics with experimental successes have to be incorporated, contained, and explained by string theory, which it cannot do if it is limited in any way, I suppose. So this thing that they're mentioning, the high sensitivity to the number of independent dimensions, is one of the big things that they found. If they can just do away with that limitation and allow for more spatial dimensions than the ones we know of or experience or can test, then that problem is kind of solved. The negative probabilities arose from a mismatch between what the theory required and what reality seemed to impose. The calculations show that if strings could vibrate in 9 independent spatial directions, so instead of 3 independent spatial directions, X, Y, Z, like what we usually are familiar with, this is saying we could maybe have 9 independent spatial directions. So not infinite independent spatial directions, but 9. 9 is more than 3, but it's also not infinite. All of the negative probabilities cancel out when we have 9. So this is why they needed 9 spatial dimensions. It's not arbitrary, or it's not like unspecific why they came up with 9. It has to do with these negative probabilities, which got them in hot water with quantum mechanics, okay? And they have to satisfy quantum mechanics. Sachi! Hi, Sachi Mama. They have to satisfy quantum mechanics because partly, or not partly, a big part of what's going on here is to unify string theory, is to unify quantum mechanics with GR and electromagnetism, have a theory of everything. So they need to explain quantum mechanics. They can't just ignore quantum mechanics, right? There's no point because even if you don't like quantum mechanics for whatever reason, as a classical physicist, you still have to acknowledge it, still have to explain it, because those things about quantum mechanics exist and they already experimentally existed. They were already shown with experiments. So you have to explain quantum mechanics, and those probabilities associated with quantum mechanics need to be numbers between 0 and 1 and not become negative or infinite. And so they found to do that, they needed 9 spatial independent directions, okay? All of the negative probabilities then canceled out. How nice, how nice. The math, just maths. String theory math. Hello, Sachi. Thank you so much for coming into the live with your zoomies. Well, that's great in theory, but so what? If string theory is meant to describe our world with 3 spatial dimensions, we still seem to be in trouble. But are we? Taking a more than half-century-old lead, as in the Kaluza-Klein work back in 1919, which injected 1 extra spatial dimension, remember? So they took that lead. 50 years later, we see that Kaluza and Klein provide a loophole. Just a loophole, hopefully, not a wormhole. Who knows? Who knows? Since strings are so small, not only can they vibrate in large extended dimensions, they can also vibrate in ones that are tiny and curled up. Sachi Mama, look at Sachi Mama. She is having extra zoomies. Let me show you. I don't know if you can see. I'll show you in just a second. Let me finish up this paragraph. And thank you so much for the hearts again, Lover Toy Pups 4. Thank you so much for being here. If you're listening to us while falling asleep, then we very much appreciate you taking the time and using this live stream as a calming effect on your sleep, and hopefully you find this to be restful and peaceful. And thank you so much for being here. We're almost done. We will show you some kitty cat and pictures in a little bit. Oh, hi Sachi. Let me show you right now, actually, because she's so cute right now. So very cute. There is Sachi Mama. Oh. He. Sachi. So, now this is messed up. Okay. So, Kaluza and Klein had provided a loophole because since the strings are so small, not only can they vibrate in large extended dimensions, they can also vibrate in ones that are tiny and curled up. So Kaluza and Klein had given permission back in the day to basically incorporate extra curled up tiny dimensions. And if you're allowed to do that, well, then you can make your strings vibrate in those extra curled up tiny dimensions as well. And vibrating in more independent dimensions was kind of needed to make the math to math and to make those negative probabilities go away, okay? With namely 9 spatial dimensions instead of the 3 that we usually think about. So we can meet the 9 space dimension requirement of string theory in our universe by assuming, a la Kaluza and Klein, that in addition to our familiar 3 extended spatial dimensions, there are 6 other curled up spatial dimensions. In this manner, string theory, which appeared to be on the brink of elimination from the realm of physical relevance, is saved. Moreover, so if they continued to have negative probabilities, then string theory would have died, okay? But they saved themselves with the extra dimensions, the 9 spatial dimensions, where 3 of them are the extended familiar ones that we all know and love, like the X, Y, and Z dimensions, and 6 of them are curled up little invisible tiny ones that we can't probe, can't test, but maybe they exist. According to string theory, they do, if you want to explain everything with string theory. In this manner, string theory, which appeared to be on the brink of elimination, and by the way, string theory is a candidate for grand unification. It is a candidate that is considered and everything like that. It cannot be tested, so too bad and so sad about that. But also, the thing is that it would have died by now if it continued to provide sort of results and outcomes and answers that are not allowed by quantum mechanics, because it's trying to unify quantum mechanics, and GR means that it has to give us answers that make sense in quantum mechanics. So it saved itself with these extra dimensions, and so extra dimensions are a requirement in string theory. So if you don't like this idea of the extra dimensions, the hidden dimensions, then it's going to be very difficult to accept string theory. I understand, but it is a requirement in string theory. So in this manner, string theory, which appeared to be on the brink of elimination from the realm of physical relevance, is saved. Moreover, rather than just postulating the existence of extra dimensions, as had been done by Kaluza-Klein and their followers, string theory requires them. For string theory to make sense, the universe should have 9 space dimensions and 1 time dimension, for a total of 10 dimensions. In this way, Kaluza's 1919 proposal finds its most convincing and powerful forum. So whatever Kaluza started in 1919 in terms of his extra 1 spatial dimension now is extended to having 9 spatial dimensions total, with 3 being the familiar ones, and then 6 extra hidden curled up small ones, and then the 1 time dimension, so total 10 dimensional. So string theory or superstring theory is a 10 dimensional with the 9 spatial dimensions and 1 time dimension. Out of the 9 spatial dimensions, 6 are the curled up ones that string theory proposes, and not only proposes, requires, because otherwise those vibrations just don't vibrate properly and come up with negative probabilities in quantum mechanics, which are not allowed. So that's sort of the basis of string theory. It's extra dimensions, hidden dimensions, higher dimensions, whatever you want to call it, which string theory does require. Somebody had been complaining about string theory being a sort of a work of fiction. I understand the frustration with string theory not being testable. Indeed, you cannot test it experimentally. We cannot probe those extra dimensions experimentally, which makes it tough to accept string theory completely for many. You're not alone if you're in that boat. But at the same time, it is a powerful candidate for grand unification, as it unifies GR with quantum mechanics, which other theories have struggled to do or failed to do. And that's kind of where things are. So is string theory wrong? We don't know. Is string theory right? We don't know. Is string theory testable? Indeed, no. And somebody had mentioned about infinite dimensions. It's not infinite. It's only 10 dimensional. Only. Just the 9 spatial and the 1 time dimension, and really only 6 extra dimensions only, and then and there you have a deal. Okay, so string theory makes us go beyond our imaginations a little bit, and requires, not just proposes or hypothesizes or mildly suggests, but requires 6 spatial curled up tiny dimensions that we cannot probe in order to explain everything about everything. And there you have it. Okay, so that, ladies and gents, was a bit of string theory for you today. Specifically about its extra dimensions. We had talked about how you also kind of need supersymmetry in string theory, particularly, of course, superstring theory, and let it kind of succeed with fermions and such as well in a different live a couple days ago. I think it was a couple of lives ago. So you can catch that as well. So definitely catch our supersymmetry live, which talks about supersymmetry. This live, we talked about string theory and extra dimensions. We have also kind of talked about the dimensions in a couple other lives as well. Okay, so for a few lives now, we've been talking about related fields, string theory and related physics. So hopefully you've been enjoying. Please do leave your comments and chat messages. Thank you so much. Completely Insane says you put it breathtakingly. Thank you so much for being here. Welcome so much, and thank you so much for being here and for participating. And if you see this as a video upload later on under the live tab of this channel, I do hope that you will like it and comment and leave your thoughts and anything you have to share, really. Like, you don't have to be thrilled with string theory at all in order to participate in these lives or these videos and comments. I am not an advocate nor an expert on string theory. That it was not my background at all. I'm simply I'm just adjusting the phone here, the location of this can here. I'm simply studying it here with you and sharing the knowledge from books and references and authors of string theory. So this book that we referenced today is The Elegant Universe by Brian Greene, a string theorist. So I'm not a string theorist myself. So